So we're going to pick up again with computer systems, sequential logic. We talked last time about why do computer systems matter. We talked about memory devices. We used memory devices to build finite state machines. And then we talked about state machine design. We did an example with the 2-button door lock. Remember, we were pressing and releasing a button, and that would unlock the door. And we put that into our pseudocode implementation, where we had a synchronizer to make sure that everything was on the same clock signal. We had our next state logic, we had our memory, and then we had our output logic. So what we want to do is we want to now talk about how to take a existing state machine design and reduce it to a lower level of complexity if possible, or make it more efficient. So we want to talk about how to remove extra states. So how do we define an extra state? Well, an extra state is going to be defined here in terms of equivalence, but think about a large state machine for, say, your project. You could have something on the order of, for instance, 70 states, which I saw in a couple semesters ago with a different student group. And if you've got that many states, you've got a lot of different memory bits. Remember, a lot of memory bits is going to require a lot of flip-flops and a lot of combinational logic to get the next state and a lot of output logic. And so if you go through all of that logic, you've got a lot of logic gates, and whether they're implemented in individual logic gates in hardware, or whether you're going to implement them in an EPLD, or whether you're going to write the software, it makes for a lot of stuff. One way or the other, you're paying for it in terms of cost. You're paying a cost for a lot of individual gates, a lot of room within your chip, or a lot of lines of code that you're going to have to write and then debug. In any case, we'd like to be able to reduce that complexity, which reduces our cost, without changing any of the functionality. So, for instance, I've got a bunch of states shown here on the left, and we're going to show that we can take that down to only 10 states. Or not even 10 states, sorry, 7 states. S10 is the last one there. And if we take it down to 7 states, we've reduced the number of flip-flops needed, we've reduced the number of lines of code needed. And so the way we're going to do this is we're going to identify and combine equivalent states. We still have to define equivalent states, but we're going to find these equivalent states, we're going to combine them, and that will reduce our total complexity because now we've got fewer states to implement. So for instance, if I've got these 3 states, S0, S1, and S2, S0 and S1 both have outputs of 0, 0, 1, 0, and they both transition to state S2. So we are going to define that as equivalent. They are equivalent states because they have the same output and equivalent next states. If they are equivalent, we can combine them, and we'll call it S0 prime with the same output, 0, 0, 1, 0, and it goes to the same next state, S2. So that's all we're doing. We're going to find all of the equivalent states. They're the same outputs, same next state, and that will allow us to have less flip-flops or less lines of code, one or the other, more opportunities for don't cares, and it'll reduce the number of gates for implementation if we chose to go that way again, or less code to write and debug. And that's the big one, is debugging. So we're going to do this in an algorithmic fashion. We're going to start with the state transition table. We will identify states with the same output, and then check for those that have the same output, do they have the same next state, and if they do, we will combine them. And then we'll just keep repeating. And after a couple passes through the state transition table, we'll find that we're not hitting anything else that's the same, and we'll know that we're done. So let's do an example. I've got a system. It's going to read input X. We're going to read 4 at a time, and we're going to check those 4 and see if they match a predefined pattern, and if they do, we'll generate an output Z. So this is kind of like your digital lock. We're going to be reading 4 inputs. These are kind of like the 4 dip switches. Do they match or do they not? And in this case, the 4 outputs, or the 4 inputs, are going to come 1, 2, 3, 4, 1, 2, 3, 4, rather than all at once. And so I've got my 2 predefined combinations are 1, 0, 1, 0 and 0, 1, 1, 0. So in my diagram here, each state has arrows out, and this is just a different representation, but the number to the left of the slash is the input X, the number to the right of the slash is the output 0. So you can see that the first state there, the first circle, is going to go to the left if X is a 0, to the right if X is a 1, and both times Z is a 0. Down at the bottom, you can see that there's only a couple that are going to have Z is going to be 1. So let's label them S0, S1 and 2, 3, 4, 5, and 6, 7, 8, 9, 10, 11, 12, 13, 14, 14 different states, 15 different states. We got a lot of states. We can trace this through. If we get a 0, 1, 1, 0, then you can see that the first one is a 0. We'll go to the left. The second one's a 1. We'll go to the right. We'll go to the right again. We'll go to the left again. And the output is a 1. There's my output 1 there. If I get a 1, 0, 1, 0, I'll go to the right. I'll go to the left. I'll go to the right and the left. And again, output is a 1. Anything else is going to result in an output of a 0. So, looking at this, there's got to be a better way. There has to be a better way to implement this, and of course there is. And I would say that there's not always a better way, but usually you can find something, some states to be reduced. So let's look at our state transition table. So in each one here we've got our current state, and this is, again, a slightly different representation than what you've got. We've got our inputs, we've got our current state, we've got our next state, and our next state in this case is broken down into our next state for each of the possible inputs, and our output, again, for each of the possible inputs. So if we start in S0, then our next state is either going to be S1 or S2, whether X is a 0 or 1, and our output is going to be 0, 0. So flipping back here, S0, that's our first one, goes to the left or the right, depending on whether X is a 0 or a 1, so it's going to go to 1 or 2, and in both cases the output is 0. And we can go all the way down the table. What you can see is that there's 2 down here that have an output of a 1 if X is 0 or a 0 if X is 1. And those are our final states on the 2 paths that we traced out. And so those 2 are both going to return to the same next state, and they have the same output. And so by our definition, they must be equivalent. And so we will name this new combined state S10 prime. And so we'll go back up to everywhere that we found an S10 or S12, and we'll replace it by an S10 prime. Well, we can do the same thing again. So now S10 prime is in there. It's in there as a current state. It's in there as a next state. And we'll go through the whole thing. And notice now that if we look at that last input block, that we got a whole bunch of things that returned S0 and have outputs of 0 and 0. Well, if they have the same next state and the same outputs, they must be equivalent. So we'll call that S7 prime. And again, we'll then go replace everything in our next state block up there with an S7 prime. So I've got now my S10 prime, my S7 prime, my S10 prime, and my S7 prime. Well, if I look at my next grouping there, my 2-digit inputs, then I've got a whole bunch of states that go to S7, well, sorry, not a whole bunch, just 2 states that go to S7 prime and have 0 output, and I've got 2 states that go to S7 prime or S10 prime and have 0, 0 output. So I'll grab one of those and combine it and call it S3 prime. I'll grab the other one and call it S4 prime. And so then my overall state machine has fewer states. It's only got 7 states now. And this is how we arrived at this one. So in this case, you can trace it through for our 2 different inputs. If we get a 0, 1, 1, 0, we're going to go left, right, down, and left. If I get a 1, 0, 1, 0, I'll go right, down, down, and left. And there we go. We've got a reduced state machine. It's got fewer states, so it's going to take fewer lines of code or fewer flip-flops and fewer logic gates for implementation, but it does exactly the same thing. It still has the same output. So we can do this with any state machine. It's not always going to result in any substantial gains, or it might result in tons of gains. It's going to really depend on the particular state machine. but at least you can always follow the same process to get through here. So the process again, state transition table, identify states with the same output. If they go to the same next state, they're equivalent. Combine them into a new renamed state, and then repeat. And you just keep repeating until nothing else is being combined, in which case you must be done. We have another method we call the implication table. It does exactly the same thing, but is a slightly different way of looking at it, and sometimes a different perspective is helpful. So again, we're going to identify and combine equivalent states, and we're going to repeat until all equivalent states are found, and our implication table is going to look something like this. So how do we draw that? Well, we're going to draw one square for each combination of states taken two at a time. So we've got a bunch of states, Si, Sj, and we're going to go through the chart from top to bottom and left to right. However, I think you can see that state S0 and S0 up here, well, that's pretty pointless. And actually all the way down the diagonal is pretty pointless. And everything above the diagonal is pointless because it's a repeat of things below. And because we're always just taking two states together, we're not worried about the order. So that's how we arrived at that, that bottom left portion. So there we go. There's just the reduced portion that has each of our states, and we don't need to go through any doubles. So how do we use it? Well, if the outputs are different, i.e. they can't be combined, they are not equivalent, we'll mark it with an X. If they can possibly be combined because they have the same output and we just don't know about the next states yet, we'll write down the implied state, the next state, for their input combinations. So if we've got our table here, and we know, for instance, that S0 goes to S1 when X is 0, or S0 goes to S2 when X is 1, and S1 goes to S3 when X is 0, and S1 goes to S4 when X is 1, then we'll fill in our table with a S1, S3, S2, S4. And that reminds us that there is our X equals 0. Oh, I did this wrong, didn't I? Sorry. There is our X equals 0. There is our X equals 1. Let's see if I can change colors here. There is our S0. There is our S1. So there we go. That's kind of what we're looking at. We're looking at the next states associated with our input combinations for each of them. And what we're looking for is, are they the same? If we've already put an X in there, then we know that the outputs are not the same. So we don't need to consider it anymore for combining. But if we haven't put an X in and we put in the implied states, then we can start worrying about, are the next states going to be the same? So if the square contains a next state pair, and that one goes to an X, well, then they're not the same, so the one that we're looking at is also not the same, and we can put in an X. And we just keep going through until everything is X'd or having identical next states, and if they have identical next states, we combine them. So in the previous one, in the previous example, the previous method, we went through and we found the equivalent states. In this case, we're going through and we're finding the not equivalent states. So let's go through a very similar example to last time. We're going to read inputs 3 at a time instead of 4 at a time, just because it reduces the number of combinations we have to look at and simplifies the example. And again, if we get a 0, 1, 0 or a 1, 1, 0, then we're going to say that that is going to have an output of 1. Otherwise, we'll have an output of 0. So here's our state transition table, exactly like the last one, and just looking at it based on what you've seen already, you can say, hey, well, those two are going to be equivalent, and these two are going to be equivalent, and then there should be another equivalence here on the next lineup. But that's what we're looking for, is we know that we're going to find that S4 and S6, S3 and S5 are going to be equivalent. So let's prove that using the state implication table. Here's our implication table. So right away, I know that S4 has different outputs from S0, S1, S2, S3. Flip back here so you can see it. S4 this one, has different outputs from everything other than S6. S6 has different outputs from everything other than S4. So, because we have outputs that are different, then we put in the X's. Because right away we know if the outputs are different, they're not equivalent states. Next thing, we write in all of our implied states. So S4, let's see, these were all done because of outputs being different. We'll go through the implied states. S2 and S4, we know they have different outputs, so they can't be combined. Well, S0 and S1 can't be combined because S2 and S4 are different. So we put in our X. And now we go down to the next one. S2 and S0 is that next square, and S2 and S6, the next states in there, also can't be combined, and so we can keep on going through. And after you go all the way through, what you're going to find is the only thing left are going to be the S1, S2 block, the S3, S5 block, the S4, S6 block. And remember, we said from looking at it that we expected S4 and S6, S3 and S5 to be combined, and notice that right now they don't have X's in them, so we've said that they're not, we have not yet said that they're not equivalent. And if you look at these states, they're all the same. Well, if those are all the same, then we must be able to combine them. And if we can combine them, then S4, S6 are combined, S3, S5 are combined, then these have the same next states as well. So S3 and S5, S4 and S6 are equivalent. S1 and S2 must also be equivalent. And so we get our state reduction. So in this case, we went from 7 states down to 4 states. It's exactly the same results as the previous method. It's just a different way to visualize it. In the previous method, we started with, hey, what's the same? And in this method, we started with, hey, what's different? So we've got 2 different methods. Both of them result in reduced order, reduced complexity of our state machine, reduced cost to implement, reduced cost to debug, and that's a good thing. So in general, you'll want to do state reduction. If you don't do state reduction, all you're doing is you're costing yourself more. It should be equivalent before and after state reduction, but it's a good idea to do it. So with all that said, our next topic is going to be system interfacing. Interfacing between mechanical and electric systems, interfacing between computer system and computer system, between all systems with power. Yeah, we're going to talk about system interfacing, and that will start on Monday.